Welcome to the lecture on integration by parts. Every differentiation rule has a corresponding integration rule. For instance, the substitution rule for integration corresponds to the chain rule for differentiation. The rule that corresponds to the product rule for differentiation is called the rule for integration by parts. Now, if we recall, the product rule states that if f and g are differentiable functions, then we have that d by dx of f of x times g of x is simply equal to f of x times g prime of x plus g of x times f prime of x. In the notation for indefinite integrals, this equation simply becomes the integral of f of x times g prime of x plus g of x times f prime of x dx, which simply equals f of x times g of x. Or what we can simply say is that the integral of f of x times g prime of x dx plus the integral of g of x times f prime of x dx is equal to the product of f of x and g of x. We can rearrange this equation as follows. So we have the integral of f of x times g prime of x dx is equal to f of x times g of x minus the integral of g of x times f prime of x dx. Now this formula is called the formula for integration by parts. And it's perhaps easier to remember in the following notation. If we let u be equal to f of x, and then if we let v be equal to g of x, then the differentials are simply going to be du equals f prime of x dx, and dv is simply going to be equal to g prime of x dx. So by the substitution rule, the formula for integration by parts simply becomes the integral of u dv equals uv minus the integral of v du. This will be our formula for integration by parts. Let's take a look at some examples. Of course, if we were asked to find the integral of sine of x dx, we know this is a very elementary integral. We've seen this in the past in Calculus 1. This simply becomes negative cosine of x plus an arbitrary constant of c. But now, let's say we want to find the integral of x sine of x dx. Well, the presence of products in the integral often suggests integration by parts. We split the product of x sine of x into two factors, one of which must be identified as u and the other as dv. The latter always produces the differential dx. Powers of x are often good choices for u. The choice of dv should be easy to integrate since it produces the function v on the right side of the integration by parts formula. Now sometimes it's kind of tricky to figure out what should your uv and what should dv be. But if you remember this, which of course spells the word late. L stands for logarithmic. A stands for algebraic. T stands for trigonometric. And E stands for exponential. We also have to include a letter I in here, and I stands for inverse trig, or inverse trigonometric. Now the key idea behind this late word with, of course, the I in it, is as you work from left to right according to late, including the I, the first function that appears in the integral will be your choice of u, and then the second will be your choice of dv. So let's see how this late method works for the integral of x sine of x. So let me just copy this down here again. We have x sine of x dx. Well, here we don't have a logarithmic function. We also don't have an inverse trigonometric function. But we do have an algebraic function, and the algebraic function is simply x. So if I let u be equal to x, of course du will simply be equal to dx here. Next, I do have a trigonometric function that's simply sine of x. So my dv choice will simply be the sine of x dx. Now, of course, how do we get the v? Well, what I like to do is I like to write an integral here, an integral here, and of course the integral of just dv is simply going to be v. The integral of sine of x dx, that's simply going to be negative cosine of x. So now I have all my pieces, and I can use the formula for integration by parts. The first part of the formula says to take the product of u and v. So that's simply going to be x times negative cosine of x minus the integral of v times du. So that's just going to be negative cosine of x dx. So right here, this is my u, this is my v, so that's the product, and then minus the integral of v times my du, which is simply dx. Of course, this simply becomes negative x cosine of x plus the integral of cosine of x dx. Now, of course, the antiderivative of cosine is simply sine. So my final answer is going to be negative x cosine of x plus the sine of x plus my arbitrary constant of c. Now, of course, I can check my answer. So if I take the derivative of this, so I'm taking the derivative of negative x cosine of x plus a sine of x plus arbitrary constant of c, I have to use a product rule. So negative x, my derivative of cosine is negative sine, plus derivative of negative x is just negative 1, cosine of x plus my derivative of sine, which is simply cosine of x. Derivative of a constant is simply 0. Now this, of course, just becomes x sine of x, as the cosine of x with this negative cosine of x add up to 0. So I do get back the original. Let's take a look at another example. Let's say we want to find now the integral of x e to the x dx. Okay, I don't have a logarithmic function, nor do I have an inverse trigonometric function, but I do have, again, the algebraic function of simply x. So my natural choice for u will simply be equal to x. And of course my du will be dx. I don't have a trigonometric, but I do have an exponential. So my natural choice for dv will simply be e to the x dx. If I find the antiderivatives of both sides of this equation, I'm going to get v is equal to e to the x, because the antiderivative of e to the x is just e to the x. So now, using integration by parts formula, I'm going to take the product of u and v, so this is going to be x e to the x minus the integral of v du, so that's going to be e to the x dx. Well, the antiderivative of e to the x is just e to the x, so my final answer will be x e to the x minus e to the x plus my arbitrary constant of c. And of course, I can check my answer if I take the derivative of x e to the x minus e to the x plus the arbitrary constant of c. Using product rule, I'm going to get x e to the x plus e to the x minus e to the x. This is simply going to be equal to x e to the x. Okay, let's take a look at this one. I want to find the integral of the natural log of x dx. Okay, well, here we don't have much choice for u and v. According to the late method, I do have a logarithmic function, so I'm going to say u is going to be equal to the natural log of x. Then, of course, du, the derivative of natural log of x, is just going to be 1 over x dx. Let's say dv is simply equal to whatever I've left over, which is simply dx. So the antiderivative is simply going to be v for that side, and for the right side it's just going to be x. Okay, let's use the integration by parts formula. So I'm going to have x, natural log of x, minus the integral of v du, so that's going to be x times 1 over x dx. This is simply going to be equal to x natural log of x minus the integral of simply 1 dx. The integral of just 1 dx, or simply dx, is simply going to be x. So I'm going to get x natural log of x minus x plus my arbitrary constant of c. Let's check this to make sure it's right. So I'm taking the derivative of x natural log of x minus x plus the arbitrary constant of c. So by product rule, I'm going to get x times 1 over x plus the natural log of x minus the derivative of x, which is simply 1, derivative constant is 0. This is simply going to be 1 plus the natural log of x minus 1, which will give me back the natural log of x. Okay, let's take a look at another example. Let's say we want to find the integral of natural log of x quantity squared dx. Okay. Well, here again, we don't have much choice for the u or the dv. According to the Light method, we do have a natural log. So let's say that u is equal to natural log of x, of course, quantity squared. Now we need to take the derivative of this thing. So using chain rule, du is going to be equal to 2 the natural log of x times the derivative of natural log of x, which is simply 1 over x dx. This, of course, is equal to saying 2 natural log of x over x dx. Let's say dv is whatever we have left over, which is simply dx in this case. So v is going to be equal to x. Okay, let's see what we get. So taking the product of u and v, this is going to be x times the natural log of x quantity squared minus the integral of v du. So that's going to be 2 times natural log of x over x times x dx. This, of course, is going to be equal to x, parenthesis, natural log of x squared, minus the integral of 2 natural log of x dx. Now, of course, you can put this 2 out in front. So that's what I'm going to do. So let me erase this, and I'm going to put the 2 out in front. So I'll have 2 here, and then the integral there. Okay. So now, we actually just did this problem on the previous example. This now turns out to be x, natural log of x quantity squared, minus 2, I'll put in parentheses here, x, natural log of x minus x, plus an arbitrary constant of c. This is the same as saying x, natural log of x squared, minus a 2x natural log of x, plus a 2x, plus an arbitrary constant of c. Okay, let's take a look at this example. Say we want to find the integral of sine inverse of x dx. Okay, so notice here we don't have a logarithmic function. We do have, of course, the inverse trigonometric. So our choice of u is simply going to be the sine inverse of x. Now, the du, we have to remember this from Calculus 1, derivative of sine inverse of x is going to be 1 over the square root of 1 minus x squared dx. Let's say dv is whatever we have left over, so that's just dx. V will be equal to x. So, using the integration by parts formula, we're going to get that this will be x sine inverse of x minus the integral of x over the square root of 1 minus x squared dx. So now what we need to do is we need to find what the antiderivative is of this. Okay, let's do some work on this side. So let me go to a next slide and then we'll come back. So let me rewrite the problem. We have the integral of x over the square root of 1 minus x squared dx. So if we use u substitution, so let's say u is equal to 1 minus x squared, du is simply going to be equal to negative 2x dx, or simply negative a half du is going to be equal to x dx. So now this is the same thing as saying negative a half the integral of u to the negative a half du. Now, of course, we need to find the antiderivative. So this is going to be negative a half u to the negative a half plus 1 over negative a half plus 1 plus our arbitrary constant of c. This, of course, becomes negative 1 half u to the positive 1 half over positive 1 half plus c. This is, of course, the same thing as saying negative u to the half plus c. And, of course, if we substitute our original u back in, this is going to be negative 1 minus x squared to the half plus the arbitrary constant of c. So now we can put everything back together. Let's go back. So this is now going to be x sine inverse of x minus negative parenthesis 1 minus x squared to the half plus that arbitrary constant of c. And of course this is the same as saying x sine inverse of x plus parenthesis 1 minus x squared to the half plus our arbitrary constant of c. Okay, let's do one more example where you have to use the fundamental theorem of calculus. So let's say we want to find now the definite integral between 0 and pi of x squared, the sine of x, dx. Okay. So, don't have a logarithmic function, don't have an inverse trigonometric, but we do have the algebraic function. So our natural choice for u should be x squared. Du in that case will simply be 2x dx. Our dv will be the sine of x dx. So v will simply be equal to negative cosine of x. Okay, so now, putting everything together, we're going to get negative x squared cosine of x. And of course, we're going to evaluate this between 0 and pi, plus 2 the integral between 0 and pi of x cosine of x dx. Now, if you notice here, we need to use integration by parts again. So if I say u is going to be equal to x, du is simply dx, my choice for dv will be cosine of x dx. V will be equal to the sine of x. So I'm going to get now that this is going to be negative x squared cosine of x evaluated between 0 and pi. We'll do that in a moment. Plus 2, in big parentheses or brackets, however you want to do it, x sine of x evaluated between 0 and pi minus the integral between 0 and pi of simply sine of x dx. That's just using integration by parts twice. Now, of course, the antiderivative of sine is negative cosine. So, I'm going to write everything together now. This is now going to be equal to negative x squared cosine x plus 2x sine of x plus 2 cosine of x. I'm evaluating everything between 0 and pi. Okay, now let's evaluate each piece step by step. Let me just rewrite the antiderivative that we found on the previous slide again here. So we have negative x squared, the cosine of x, plus 2x sine of x, plus 2 cosine x from 0 to pi. Okay, so now using the fundamental theorem, I'm going to get negative pi squared cosine of pi plus 2 pi sine of pi plus 2 cosine of pi minus, of course, 0 squared cosine of 0 plus 2 times 0 sine of 0 plus 2 cosine 0. Now we know that the cosine of pi is negative 1, so I'm going to get negative pi squared times negative 1. The sine of pi is, of course, 0. So this is going to be plus 0. And the cosine of pi, again, is negative 1. But with the 2 on front, I'm going to get negative 2. Zero squared times cosine of 0, that's simply going to be 0. 2 times 0 times sine of 0, that's going to give me another 0. And then the cosine of 0 is 1. With a 2 in front, that's going to give me a positive 2. So this simply boils down to being positive pi squared minus 4.